Hey guys, welcome to today's class. Have fun.
Hello. Today I'm making use of two reference textbooks, New School Physics and Essential Physics. So today I'll be taking the topic Fundamental and Derived Units, as well as Fundamental and Derived Quantities, and lastly, Dimensional Analysis. So the three most important basic quantities in physics are length, mass, and time. Length can be defined as the extent of space or distance extended. Talking about length, we have a point A and a point B. The distance traveled in a specified direction when measured is referred to as the length of that body which traveled that distance. Also, we have mass. Mass is commonly defined as the quantity of matter or material substance present in a body. So, when you talk about mass, you have a body on a weighing balance. The measurement taken here is referred to as weight. Why? Because gravity acts on the body. So this is weight. Whereas mass refers to the quantity of matter this body tends to carry. So that's what we refer to as mass. They are a bit similar to each other. Mass is measured in kilogram. Lastly, we have time. Time is defined as that in which events are distinguishable with reference to before or after. So time is just the period in which events occurs. We have so in summary, the basic and most fundamental quantities are length, mass, and time. So now we're looking at fundamental quantities. Fundamental quantities are basic quantities that are independent of others and cannot be defined in terms of other quantities or derived from them. What does that simply tell us? Fundamental quantities are the basic quantities, that is, they are primary quantities. No other quantity is established without fundamental quantities. Like the name implies, fundamental, they are primary quantities. They are basic quantities upon which most quantities depend, if not all of them, but most quantities depend on fundamental quantities. So similarly, fundamental units are basic units upon which other units depends. So what we simply have is when you have a quantity, that particular quantity have its units. So here we have basic, the fundamental units examples in a table. We have length, which the unit is in meters. You have time, it's in second. You have mass, which is in kilogram. So that's tell us the first three, which is length, mass, and time. These three are referred to as the basic of the fundamental quantities. So we also have electric current, temperature, amount of substance. We can also have luminous intensity. So you can see here that each quantity has its own units, meter, second, and so on. And they also have their abbreviations. So the units in this table are in SI units. SI, which is System International, is the most important system you see today, which is the most acceptable system of units in physics and all physical quantities that we see around us. Also, when we talk about derived quantities, like the name implies, derived quantities are those obtained by simple combination of the fundamental quantities. So when you take one or more fundamental quantities and you combine them, you're going to have a derived quantity. And I said earlier, every quantity has its units. So a derived quantity would also have its derived units. So these are examples of derived quantities. You have area, derivation, length times breadth. You have volume, length, breadth, height. So these are examples of derived quantities. I'll be taking us through how these formulas were derived from the fundamental quantities. So on getting to dimensional analysis, which is another part of this class, I would explain the derivations which we see here. These are basic knowledge which we are fond of. So, having been able to establish what fundamental quantities and derived quantities are, we can sum up the difference or characteristics of these two quantities. Fundamental quantities are generally accepted quantities. Like I said earlier, they are basic quantities, so they are generally accepted. Derived quantities are just accepted. Derived quantities are formulated from fundamental quantities. So, in as much as they carry out the necessary formulas or equations they are meant for, and they are derived from fundamental quantities, so they are also going to be accepted. So, the fundamental quantities are based on international system, which is the SI units of measurements. So these fundamental quantities are based on the SI units. So derived quantities, like the name implies, derived, they are formulated from the SI units. So fundamental quantities can stand alone. That's because they are basic, while derived quantities cannot stand alone. Fundamental quantities have direct calculations. Their calculations are derived. A simple example, the fundamental quantity is mass. Mass is simply measured in kilogram. This is fundamental. We're talking about a derived quantity. Let's say density. Density is mass over volume. Mass here is a fundamental quantity, which is in kilogram. Volume is not a fundamental quantity. Volume is a product of length, breadth, and height. So which gives us length, which is a fundamental quantity in meters, breadth, which is a fundamental quantity in meters, height, which is a fundamental quantity in meters. So which gives us kilogram per meter cube. This here is a derived quantity. Okay, so fundamental quantities are basic units of measurement. Your length is a basic unit, your time is a basic unit, and your mass is a basic unit. On the other hand, these derived quantities are not basic units of measurement. They are secondary units, secondary quantities which are derived from the fundamental quantities. So quickly, we'll be looking at some simple examples. Fundamental quantities. You have mass, you have length, and you have time. So these basic quantities are assigned symbols M, L, and T. So these symbols denote. So, like I said earlier, my reference materials are Essential Physics and New School Physics. So this is an example from Essential Physics, which I'll be explaining better. So you have a small mass suspended from a long thread so as to form a simple pendulum. The period T of the oscillations depends on the mass M, the length L of the thread, and the acceleration G of free fall at the place concerned. So we're given the relationship this, and we're asked to find the values of x, y, z, and hence derive an expression relating all these terms. Okay, so before I solve the example, the knowledge of dimensional analysis enables us to show the relationship between physical quantities. It also helps us to derive formulas So if we can derive formulas, then also we should be able to state its units. So all this we can do is as a result of dimensional analysis. So I'll be taking the solution to the example given there. Okay, so the first thing to do in any calculation, most especially in physics, is to list out the parameters you are given. Okay, so we are given a relationship which is C equals to K M raised to power X L raised to power Y and G raised to power Z. We are also told that we have a constant K which is equals to 2 pi. So we are asked to find the value of X, Y and Z and also show the relationship between these. So we can only achieve this through dimensional analysis. Okay, so I want us to recall that for mass, its dimension is m. For length, its dimension is what? It's L. So we have the mass, the length, and gravity. Okay, we have gravity. So we don't know the dimension for gravity, but we know that gravity is in meter per second square, which is acceleration due to gravity. And you can also say gravity is due to acceleration. So from the previous examples we did, I showed us that acceleration is the change in velocity with respect to time. So this gives us mass, and time is t squared. Sorry, this is meter, not mass. So this is L. So this is L over t squared, which gives us LT minus 2. So we have from this, bring it down here, we have T, K, which is our constant, which you can ignore for now. So we have M, which is, okay, mx, M, which is the mass, is M, L, which is the length, G, which is acceleration due to gravity, which I had shown here, LT minus 2 raised to power Z. This is Z. Okay, so we have to expand the bracket. We have M, X, L raised to power Y. Expanding this, the power multiplied by L gives us LZ. The power multiplied by this gives us 2 minus 2 times Z minus 2Z. By indices, we have MX, L, Y plus Z, T minus 2Z. Okay, so recall that from the question it says T is the period of oscillation of the pendulum, and recall that period is in time. So meaning that this T, it's dimensional. By dimensional analysis, it is going to be T. But since we have M, L, and T on the right hand side, we need M, L, and T on the left hand side. So all we just do is to say M is power 0, L is power 0, and T. Recall that this will give us 1 multiplied by T give us T, which is this T. Okay, so we continue. So M raised to power 0, L raised to power 0, T equals to M raised to power X, L raised to power Y plus Z, T raised to power minus 2Z. So you can see we have M on both sides, L on both sides, and T on both sides. So all we do is to take the equal bases and equate their powers. What do I mean? You have M raised to power 0 equals to M raised to power X, L raised to power 0, L, we have T here, So you can say 0 is equals to x, which is our equation 1. Here we see 0 is equals to y plus z, which is our equation 2. See 1 equals to minus 2z. So we have 3 equations here. X is already 0. We have the answer of that. We have 2 unknowns here. We have 1 equals to minus 2z. So from here we can find the value of z. 1 equals to minus 2z. We divide through by minus 2. So minus 2 cancel minus 2. We left to z. Z is equals to minus 1 over 2. Okay. So we found z to be minus 1 over 2. Substituting the value of z into equation 2, we have y plus z equals to 0. The value of z, which is minus 1 over 2, equals to 0. Plus multiplied by minus gives us minus half equals to 0. Take half to the other side. This gives us y equals to half. So we'll be able to find the values of x, which is 0, y, which is half, and z, which is minus half. So lastly, we are told to find an expression for this relationship. I told us dimensional analysis helps us to find formulas, help us to know the relationship between terms. So in this case, we are told to find a relationship between mass, length, and gravity, which I've shown in the previous example. So you recall that since x is equals to 0, y is equals to half, and z was equals to minus half. So recall also we're given the constant k equals to 2 pi. So this brings this down to this point. We have t equals to the constant k is 2 pi multiply m, which is m, the value of x is 0, multiply by l, the value of y is what? Half, multiply by g, the value of z is minus half. Now you can see we are using the expressions here, not their dimensional form, because dimension analysis helps us to use the dimensions to find unknown values, this x, y, and z. Okay, so t, so 2 pi, m raised to power 0 is 1, multiplied by l raised to power half. Recall from indices, this gives us l multiply by g raised to power minus half. So this is the same as 1 over g half. This gives us t equals to 2 pi multiply by this multiplied by 1 over square root of g. This gives us t equals to 2 pi multiplied by square root of l over square root of g. This gives us 2 pi into l over g all roots. So this is the final answer. Thanks for listening. So I advise you also try out more examples. I'll see you in subsequent classes.
I hope the class was interesting. If you have questions, please drop them in the comment section or send us an email. We will love to help you further. See you in the next class.